Back to class. Okay, so we are on the last lecture of the semester. This is something called thin films or thin film interference. And I should tell you, this is one topic that I do a little differently than the book does. And the reason is I like to actually graph things and kind of see what's going on visually. But let's see what this topic is about. And let's look at an example. So let's say you have about like water. Could be like a puddle on the ground. And you dump some oil in this. You might have seen this. If you're in a gas station and it's raining, sometimes you look down at the puddles and see like little rainbows. Why does that happen? So basically the situation is we have air, and here's our water, and there's a small amount of some substance on top. Now again, this is just one example. But a thin film, it doesn't have to be liquids at all. You could have like plastic or like glass with some coating of something. But it's called thin films though for a reason. We'll say T is the thickness of the film. And this is usually very, very small thickness. We usually measure it in nanometers just to give you some idea. So that's why it's called thin film interference. So what happens, let's say we have light shining down on this, just light shining down. So it's coming from air, it's going to hit this oil that's resting on top of the water. And we say light shines vertically downwards on the oil. However, I drew it at a slight angle, and there's a reason for that. So really, we're considering the case where light shines straight down, but then if we look at the reflection, it's going to be straight up, and we're not going to see anything. We have to draw it at a slight angle. So you can either consider it, the light actually shining at a slight angle, or straight down, but we're just introducing this angle for clarity. So what happens is we get a reflected ray. So light reflects off of this first surface, and light is also going to transmit into the oil. So we're going to have light going down into the oil, and then it's going to hit the oil-water boundary, and it's going to reflect off of that. We'll call this ray 2. Actually, you know what? I'm going to call this ray 4. For reasons that, we'll say like going from here to here is 2, from here to here is 3, and then that ray is 4. And so we're looking from above, so we're seeing a combination of rays 1 and 4. Now, theoretically, we could also consider when it hits this boundary, it's going to reflect again and then reflect off this one. And so we could have like, it could keep bouncing around. But the thing is, it loses, it's dividing every time. So we have an intensity here that's split between these two. And some of the light's going to go into the water. And so, if you consider like an extra bounce, that's not going to really contribute anything significant, so we're going to ignore that. So we're just going to look at the combination of rays 1 and 4. What kind of interference are we going to get from this? That's what we're trying to figure out. And so it all comes down to the phase. When you combine waves, the phase determines the resulting amplitude and whether or not it's constructive or destructive interference. And there's actually two things we need to consider. Now, if we look at 1 and 4, there's definitely a path length difference. We can even write that down. Delta, the path length difference, is 2 times the thickness. Now again, I said we're considering light shining down vertically. So it goes down and then it bounces down and up again. If it was at a significant angle, typically going from air to a median, it would bend towards the normal. But again, we could have a situation where light hit at a significant angle, and maybe it would do this, where the extra path length would be greater than 2t because it's not going straight down and back. There's that extra horizontal effect to take into account. Again, we're not going to worry about that. Okay, so that's one factor that's going to introduce a phase difference, just a path length difference. But there's something else we need to consider. And for this, we kind of want to go back to mechanics, like 121, when you have a wave on a string. So say we have a wave on a string. Let's do it like this. We have a string here. And let's say we create a pulse on this string. And say the string just ends. What's going to happen when it reaches the end? The pulse is going to bounce back. And it's going to look a lot like the initial pulse. A little smaller because there's energy lost and dissipated. But now what if we send a pulse and this end of the string is fixed? What happens in that case is the reflected wave comes back upside down. So here we say there's no phase shift. Here we have a phase shift of 180 degrees, or pi radian phase shift. Okay, now this phase shift only occurs when you have a reflection. Or maybe I should say it may occur when you have a reflection. So when this first ray hits, we have a reflection and a refracted ray. The refracted ray does not have a phase shift. That's important, so I'm going to write this down. So a reflection, we have a possible, I'll just write PS for phase shift. For the refraction, no phase shift. Okay. So now the question is, what determines if we have a phase shift or not? And it depends on the relative indexes of refraction at the boundary where the reflection happens. So let's say we have something like, I know I'm going to have to write down a few more equations, so I'll just leave some room there. Let's say we have a reflection like this, where this is N1 and this is N2. If we're going from a low index of refraction to a high index of refraction, we get a phase shift. So if N1 is less than N2, we get a phase shift. If N1 is greater than N2, there's no phase shift. So just remember, low index to a high index, you get a phase shift, and that's only if that's only for the reflection, not for the refracted ray. So there's one more thing we need to consider that happens when we're going to consider this, and when we look at our conditions for constructive or destructive interference, we want to compare that to the wavelength of light. Delta is lambda over 2, or delta equals lambda. That determines what type of phase shift we're going to have, or those are the extreme cases with constructive and destructive interference. It depends on the wavelength. However, we have different wavelengths to deal with here. Let's say the light has a wavelength, we'll call it lambda naught, is the wavelength in a vacuum, and I'll write that here so there's room. Now the wavelength in the film is going to be different than the vacuum wavelength. So remember, the frequency is not affected by going from one medium to another, but the speed is. Depends on the index of refraction. So essentially we're going from a vacuum to a film. And so, yeah, the wavelength in the film has to be smaller than the wavelength in vacuum, because the speed of a wave is a frequency times the wavelength. So in air, you have the frequency times the wavelength in a vacuum, or in air, basically the same thing. That equals the speed of light. Here, the frequency times the wavelength in the film is going to be a smaller number. And so it has to be, the wavelength in the film has to be smaller. If you multiply the same frequency but get a smaller number, the wavelength has to be smaller. But let's work that out. Let's say that the frequency in a vacuum equals the frequency in the film. So I'm using air and vacuum interchangeably. And that's just because n is, for air, it's like 1.0003 or something like that. Now, I should point out that the effects of air on light isn't always insignificant, because light can be scattered by particles in the air. But for what we're doing, air and vacuum are essentially the same thing. Okay. Now, for the frequency in the vacuum, that would be the speed of light over the wavelength in a vacuum. So again, we have frequency here. Frequency would be the speed over the wavelength. Had to happen at least one more time, so there we go. Okay, so yeah, frequency, speed over wavelength. So the speed in a vacuum is just the speed of light. Lambda naught is the wavelength in air or vacuum. Now for the film, we have whatever its speed is, v, divided by the wavelength in the film. Now let's solve for the wavelength in the film. So v film, that's lambda naught times v over c. Okay, and we can break this as lambda naught. If we multiply the numerator and denominator times 1 over v, we can say lambda naught divided by c over v, which is n. So what we have here is a wavelength in the film is equal to the wavelength in vacuum divided by n. Now, the index we're talking about, the n in that formula, that would be the index of refraction of the film. I didn't write that on the equation sheet, but that's what it is. Because we have c over v, that's going on in the film. Okay, so now we've got the background necessary. So we want to consider what type of interference we're going to get. And again, I like to do things graphically. So we're going to put together this picture where, let's look at this boundary here. We have the air-oil boundary. Let's say that this is the light propagating and then it hits here. This is specifically, we're plotting the wave as a function of distance. So here's our boundary. So what I mean by, this isn't a spatial plot, we're just plotting it as a function of distance because the direction of the wave changes, but we're not going to take that into account. We're just going to, as it moves, the distance just that it travels keeps increasing. So let's say we have a wave that, I should have drawn this boundary a little separately, but let's say we have a wave, and again, this is its electric field. And it's moving along, and then let's draw our boundary here. Let's call this boundary 1. Okay, so here we go. It hits the boundary, and then we're looking at the reflection. And it depends on whether or not we have a phase shift. Remember, a phase shift is a 180-degree shift. And again, like this is 360 degrees from one end of the wave to the other. So it doesn't even matter where you are. If you shift by 180 degrees, it's effectively just flipping the wave upside down. So let's just say this is a case where we have a phase shift. The reflected wave would have looked like this if there was no phase shift. But again, a 180-degree shift, that would make it look like this. And curvature right there, but yeah. So with a phase shift, it's going to look like this. Now, the only relevant part of this graph we need is just this part right in here. So we could redraw it like this. So that's what we get with a phase shift. If there was no phase shift, then what we would have is just this. It would just keep going, nothing would happen to it. So again, we're just looking at a portion of the wave, just like right at the boundary. And then it continues as a wave in both directions, but we don't care about that part, so I'm not going to draw it. So again, this is what we get with a phase shift, and this is what we get with no phase shift. And again, this is just a reflection off of boundary 1. So these are the two possibilities. Now I conveniently picked it so that the electric field, hit the boundary just like this. It doesn't have to be the case, but it doesn't really matter what phase it is when it hits the boundary. This is just the easiest to draw, so that's what I'm going with. Okay, so that's a picture we get from looking at ray 1. That's, yeah, maybe, you know what, I'm going to change these names. I'll call them A and B. Boundary A, or surface A and surface B. This way we can distinguish. Okay. So we traced this ray. It hit and then it reflected. Now we want to do the same for the next one. That one's a bit more complicated. But let's remember this result because I'm going to have to erase it. So this one's easy. At surface A, it either just hits and keeps going if there's no phase shift, or it hits and bounces off. And typically, we're only going to really be dealing with this case because we're always going to be going from air to some medium. So we're always going to be going from low to high. So picture is pretty much going to look like this for that first boundary. Now for the second picture, this one's a bit more complicated. So what's going to happen, this is just tracing the electric field as a function of distance, without regard for whether it's going up or down, like, in space. We're just going to keep following it. So what's going to happen, we're going to hit boundary A. And again, we've got an electric field coming in like this, and then it's going to enter into the film, which in this case is oil. And remember, for refractions, there is no phase shift. So again, we just keep going into the oil. Eventually, we're going to hit boundary B. And then we're considering a reflection off of boundary B. So we're looking at, here, this is ray 1. So right here is ray 2. And then after it hits B, it bounces back. So the next thing it's going to do is hit A again. And then it's going to come out into the air. So this is region 1, 2. Here, let's do it like this. Okay, so again, well, let's just take this ray. So this is ray, we're considering like this segment to be segment 1. Oh wait, that kind of, maybe I should come up with yet another way to do it. You know, let's use lowercase letters. I want to be clear. So this is A, B, C, and D. Okay. So this is region A, B. I'll do it on the bottom because we'll run into interference there, but. Okay. So A, B, C, and D. Okay. So again, A is this incoming wave. And then the part we're following, it enters region, the film, where we're B is between surfaces, capital A and B. Here. And then it's going to bounce off surface B and head back towards surface A. That's part C. And then it's going to come out into the air. So that would be D. Okay. Now, the question is, drawing this is fairly complicated. A couple things happen. One, usually we don't know how thick this film is. We don't know where to draw this middle, like we don't know how to even draw this picture fully because we don't know the distances here and here. And that's a complication that we can't really deal with, at least when it comes to drawing graphs accurately right now. The other thing is, remember, this is an incoming wave. So the electric field, looks like a sine wave. We're only just drawing part of it. But then when it enters this film, the wavelength decreases. And so, we'd have to decrease the wavelength depending on, whatever the index refraction of the film is. But we're looking at basically what we want to do. We're kind of going to work backwards. Let's say right now we're looking for constructive interference. So let's say we want the thickness of the film to be whatever it needs to be so that the end result is going to be constructive interference. So that's what we're looking for. So remember in this case, if we look at this first reflection, it looked like that. So if we want constructive interference, we know we have to end up with our wave coming out looking like this to match what we had for our first. So this is ray 1. This was ray 1. This is ray 4. So if we want constructive, this was reflection off the first surface, that's ray 1. I guess I could call this 2 since I changed the labeling there. But we'll just go with it. This is ray 4. And so again, if the end result looks like this, we have constructive interference. And so now we can kind of work backwards. So again, I can follow this here because there's no worry about a phase shift. Because again, going from C to D, this is a refraction. There's also a reflection back into the film. We don't care about that. So because this is a refraction, it's just a smooth curve with no phase shift. So given that we have constructive interference, which will occur for some thickness, we can draw the end of the graph. And now we just have to figure out what happens in the middle. And how we go from here depends on whether or not we have a phase shift at this second reflection. So remember, phase shifts only happen at reflections. So let's consider the case, let's make up some numbers. For water, we have n equals 1.3. Oil, I have to look up the table for oil. I picked oil because oil floats on water, so this is a realistic problem, but, oh wait. Sorry, I should have had this table up earlier, but I could look in the notes. I'm sorry, I don't know where this table is. If I can find the notes, that might be easier. Okay, sorry about that, but well, benzene, I think that's basically oil. So let's say N equals 1.5. Okay, so now we have to ask ourselves, do we have a phase shift at this boundary? So remember, if you go from a low index to a high index, you have a phase shift. Here, high to low, that means there's no phase shift here on this reflection. So what that means is we draw this electric field with nothing happens at this boundary. So we can just draw it like this. And there we go. Now again, this picture is not accurate scale-wise because, well, it's probably not anyways. We don't really know what the wavelength is, but the wavelength should shrink in here. So again, we could compress it if we needed to, but it doesn't matter. We just want to get the thickness of the film. And this is actually what we need, because remember, the thickness of the film is just the distance between, this is the thickness, going from A to B. And so we can see that this is 1/4 of a wavelength. And so we can see in this case, I'm going to call this TC for constructive interference. This is the wavelength over 4. However, we have to be a little careful here. What wavelength are we talking about? Well, this wave is in the film, so this is the wavelength of the film over 4. But we don't know what that is. We were given the wavelength in air, or vacuum, and remember the wavelength of the film is lambda naught over the index of refraction. So we can say that this is lambda naught over 4n. Okay. Now again, this result only applies to this particular setup, where we have constructive interference, and in the middle we're going from like the second reflection, we're going from a high index to a low index. What if we have, well, what about destructive interference? What if we wanted destructive interference? Let's do that. So I'm going to have to redraw this. You know what? Before we move on, I'll just go. How did I know this was 1/4 of a wavelength? Let's draw a wave. We don't need that anymore. Let's just draw a single cycle of a wave. So this is a wavelength. So going from like 1, 0 to the next, this is half a wavelength. And then let's cut one of these in half. Like going from 0 to maximum amplitude, that would then be 1/4 of a wavelength. So that's what we have here. We're going from 0 to maximum amplitude. That's 1/4 of a wave. If you go from like 0 to the next 0, that's half a wavelength. Okay, so we got constructive. For this setup, when we go from a high index to a low index, for the boundary between the sections.